Okay, guys, welcome. We have a short lesson on performing operations with calculus. So remember, when you take the square root of a positive radical, you turn out technically this is plus or minus 10, right? But a lot of times they keep the positive root when you're simplifying. In the equation, plus or minus in it. So, like if I had the square root of negative 100, that's another way of saying negative square root of, or excuse me, the positive square root of negative 1 times 100, square root of 100, which becomes I times 10, which is 10I. And so we just, once again, we keep the positive. If this wasn't an equation, we put a plus or minus 100. Okay. So what happens is if you start looking at I represents a square root of negative. I squared is negative. So I cubed is I squared times I, which is just negative 1 times I, which becomes negative I. So I to the fourth can be I squared times I squared if you wanted to. So notice I squared is just negative 1 times negative 1, which is positive 1. So notice you go from I to negative 1 to negative I to 1. So if I did I to the fifth power, I could take I to the fourth times I to the first, which is really just 1 times I, which is just I. So it repeats. You get I again that pops up. So if I did I to the sixth, so that would be I to the fifth and I to the first. And I to the fifth is I times another I, which is I squared, which is negative 1. So notice that's the second one. So if I did I to, that would be I to the sixth times I to the first. Since I to the sixth is negative 1 times I, you're going to get negative I, which is the third one repeated. And if I get I to the eighth, you got I to the seventh times I to the first. I to the seventh is negative I times the I becomes negative I squared. Because I squared is negative 1 times the negative out front makes it just 1. So notice that's the one that's repeated. So an easy way to remember this, guys, is so they always keep repeating. Every four powers they repeat. So I is like a plus one over, or actually a plus zero. A plus zero. Okay. Or no, that would be a plus one over. Yeah. So we're good. And I six would be a plus two over. And I to the seventh is a plus three over. And then the I to the eighth goes back to I, or back to one. Because notice that right here, that's back to one. I goes back to one. All right. So with that being said, I named, to the 11th. An easy way to figure that out is every four they repeat, right? So I to the eighth would be the lowest one underneath. So 11 is a plus 3. 11 is 3 over every. right? 3 over a multiple of 4 is multiple of 4. So what I could do is I could negative number right away. If I wanted I to the, see, 20 is an even multiple of 4. And so all the powers are 4 to 1. The fourth is 1, I to the 8 is 1, so that means this is also 1. That means I to the 24th is 1. But I to the 23rd would be considered a plus 3 over 20. So that means a plus 3 is negative I. So I to the 21st would just be a plus 1 over 20. That's a plus 1 over a plus 4. So therefore, plus 1 is just going to be I. So that's how you take power. Okay. All right. So let's go ahead and, so notice the square root of 20 is the square root of negative 1 times the square root of 25, which becomes I times 5, which is, so we keep the positive root of the red when we simplify. So this one would be the square root of negative 1 times 36, which becomes I times 6, which is 6I. So the challenge with this one is it's not a perfect square. So you would have to do root negative 1 times root 16 times root 3, which becomes, these two become 4I times the root 3. So the next one would be negative 5 out front times 3I, which is negative 15I. So what they'll have you do is they'll find powers of I. So you look at the power of the I and simplify all those powers first. Okay. So 44 is divisible by 4. That means it would go evenly into it. So if you look at the repeating ones, it would just be 1. So this would be replaced with 1. I to the 73rd is not divisible by 4. So what you could do is divide it by 4 to see what it is. Notice it's not there. So the nearest number underneath 73 that is divisible by 4, you can check. 72 divided by 4. It works. So that means 73 is a plus 1. So you go to plus 1 on your chart, right? So you notice that's I. So you replace I to the 73rd with I. I to the 88, divide that by 4, is even. So that's just 1. I to the 54, divided by 4, doesn't work. So you try numbers underneath it. 53 divided by 4 doesn't work. Okay. Then try 52. That works. So that means 54 is a plus 2, which means it's negative 1. So now I can simplify my expression. So notice you get 4 plus 3I plus 5 plus 7. And so now we add like terms. So now I get 9 plus 7, 16 plus 3i is your final answer. So let's do the same thing with this one. 104 is divisible by 4. So that means it's a 1. Negative 10 times 1. Remember, they keep repeating. Okay, so they keep going. Every 4, it's 1. So forth. So like if I did the next, 7 is not divisible by 4. That's a plus 3 over 4. So if you go to a plus 3, it's negative I. So it's 9 times negative I. 100 is divisible by 4. So what happens is that's a plus 1. 114 is not divisible by 4. So you check numbers right underneath it. 113 doesn't work. 112 does. Therefore, 114 is a plus 2. So that means you go to a plus 2 is a negative 1. And then we simplify. So all of these we want to take care of. Negative 10 minus 9i plus 4 plus 9. Add your like terms. Negative 10 plus 4 is negative 6 plus 9 is positive 3. So you get 3 minus 9i is a simplified form of this. So the next step is to be able to take expressions with i's in them and simplify them. So here's an example that ab cubed is your expression. A is 5x and b is negative I. So we simplify those separately. So notice negative I to the third. Think of it as like negative I times negative I times negative I. So these two become I squared times negative I. And so notice you end up with negative 1 times negative I, which is, right? Because a negative times a negative is positive. So your answer for this whole thing would be 5ix. Okay? So if I had something like this, substituted, we could do this right. So if we simplify this, what we want to be aware of, guys, is we have to write this twice because of the square. In this case, y doesn't mean anything. I is already in there, so there's a simplified form of it. Okay, so we have to do our multiplication of FOIL. Y times y is y squared. The outer terms would be plus 4iy. The inner terms plus 4iy. And the last terms would be 16i squared. Anytime you have a power of I, you simplify. I squared is negative 1. So that means this whole quantity becomes negative 16. So your final answer would be y squared plus iy's, 8 of them, minus 16. So here's where we have to be very smart when we solve quadratic equations. We see these complex numbers. So on the first one, I can solve by square rooting. And notice you get x equals plus or minus the square root of negative 16, which becomes the square root of negative 1 times 16, which is plus or minus I 4, or plus or minus 4i is how you should express that. Don't forget the plus or minus is when you're simplifying in an equation out front. So on the next example, if I subtract 2 over, x squared equals negative 100. So when you square root both sides, you're going to get the square root of negative 1 times the square root of 100, which then becomes 10i. And don't forget plus or minus. So it'd be plus or minus 10i. These mean they don't touch the x-axis. Imaginary solution at the x-axis. So if I did this example, add 10 over 2x plus 36 equals 0. I could type this into decimals and see this would not have x intercepts. However, I could see this algebraically. When I bring the 36 to the right side and then divide by 2, you get x squared equals negative 18. Then I square root both sides. So notice I get x equals plus or minus the square root of negative 1 times the square root of 18. 18 splits to 9 and 2. So your final answer should be 3 from the square root of 9, I from the square root of negative 1, and then you tack on the root 2 at the end. All right. So when we talk about this idea of a complex number, there's always two parts. There's a real and imaginary part. And so if I do this as 2 plus 3, you can actually graph complex numbers on the xy plane. They call that, so basically on the x-axis you have the real part, and the y-axis you have the imaginary part. So if I graph 2 plus 3i, you go 2 on the x and up 3 on the y-axis. That's the complex part. It's positive. And notice they meet right there. And so you could draw a vector from the origin to that spot. And that's considered how you graph a complex number. Okay. Now, I won't necessarily have you guys graph complex numbers, but I do want you to be aware you can split them up into parts and draw a little vector off. All right. So the idea of complex numbers deal with the situation where we're looking at real numbers or imaginary numbers, right? So a complex number falls under the imaginary numbers. So this is what we haven't seen much yet. So it has a real and an imaginary. So remember, imaginary numbers always has that I in them. So these are all examples of pure imaginary numbers. So a pure one would be like with an I, whereas imaginary is a real and imaginary part. Okay, so real numbers never have I, or imaginary numbers. So the next skill is to be able to simplify. So if I take the sum of two complex numbers, in standard form, what I really want to do is just add them up. So negative 1 and 3 makes 2. 2i plus 3i, 5. And you leave it with the real and then the imaginary part. So if I'm subtracting complex numbers, I distribute 2 minus 3i minus 3 plus 7i. Add like terms. Notice I get negative 1 plus 4i in standard form. In a case like this, I'm multiplying two complex numbers. So this would become negative 3i minus I squared. I squared is negative 1. A negative of negative 1 is positive 1. So this whole thing is just a plus 1. Final answer should be 1 minus 3i. Always powers of I down to the lowest one. So like the same thing on this one. 15i minus 21i squared. Because I squared is negative 1, and you're multiplying that by negative 21, that whole thing becomes positive 21. So the real answer should be 21 plus 15i. A case like this, I'm going to FOIL. 2 times 6 is 12. Outer terms, negative 4i. Inner terms, 18i. Last terms, minus 6i squared. So now I add like terms. The negative 6i squared is really positive 6. So now I add 12 and 6, get 18. Negative 4i plus 18 is positive 14i. So we have to remember to FOIL binomial. This one would be the same as this one. So if I see an example, what I have to do is multiply by what we call the complex conjugate. So remember when we did with radical and we multiply by the irrational conjugate, you're going to do the same with these. So I would have to take 1 minus I to its top and bottom. The reason you do that is because the bottoms will disappear the I stuff. So let's FOIL it. First terms is 1. Outside terms is negative I. Inside terms is positive I. Last terms would be negative I squared. Positive and negative I cancel. This becomes plus 1. Plus the 1 out front becomes 2. So I got to make sure I see that the benefit of using the complex conjugate. So on the top, I FOIL. First terms, 2. Outside terms, negative 2i. Inside terms, minus 7i. Last terms, positive 7i squared. So now, the 7i squared is a fancy way of saying negative 7. Plus the 2 out front is negative 5. So you should get negative 5, and then add these two like terms, minus 9i all over 2. And that is our answer, because if I were to split this into two separate fractions, they would not reduce. So I could leave it in either form. That's the hardest one you're going to see. So one other case that could happen is if you just had I in the bottom of a fraction. So to get rid of it, you multiply top and bottom by I. And the reason you do that is because I squared becomes -1, which is no longer technically a radical. Don't forget to distribute the I in the top. So you get I times 1 is I plus 2I squared. So notice the I squared term simplified to this one's -2 and this one's -1. So if I divide both of those by -1, you're going to get -I plus 2. Or flip it as 2 minus I in standard form. Okay. So last two scenarios is dealing with an equation with common parts that you have to set equal. So the first thing I noticed is the real parts you set equal, and then the imaginary parts you set equal. So if 2x equals 10, x is 5. If -7i equals yi, then -7 equals y. So those are very easy to get. The last type you'd like to see is when you're squaring a binomial as a complex one. So let me show you guys some steps you want to be aware of. So the first thing I do is write this twice. Because of the square. Then I FOIL from Algebra 1. First terms become √5 times √5. That's just 5. All over 2 times 2, which is 4. The outside terms would become 5 √5i. So 5 times √5. Now what I'm going to do is put the I right after the 5. So 5i times √5 all over 8. The inside terms would become 5i √5. Here's your tops. All over 4 times 2, 8. And then the last terms would become 25i squared all over 16. So now what happens is we just make sure these are simplified. So this last piece is -25 over 16. The middle terms, you're going to add like terms. So notice I get 10i times √5 over 8. And so now we got to this step. And so they want it in this a plus bi form. So this is your I part. And then these two you got to add like terms. So I'm going to get a common denominator between these two. So I'm going to show that on the side. 5/4 minus 25/16. So I'm going to multiply this one by 4. Get 20 over 16 minus 25/16, which is really 5/16. Okay, so now I get, this is the real part. The imaginary part is 10i √5 over 8. Don't forget to simplify fractions at the end if it happens. 10/8 can divide by 2. So you're left with 5i over 5 over 4. Final answer in complex form. Real plus imaginary. Okay. So what your goal for today is to practice some of those scenarios. And I want you guys to do a good job with those before I meet again tomorrow. All right. Have a good one, guys.